Welcome to our session on regression analysis. So a typical regression question looks something like this and something like this. Now, for you to understand what is involved in linear regression, I'll give you a background briefly on what regression is all about. So regression basically in economics is an analytical tool that we use to examine relationships that exist between two variables, the dependent and the independent variable. So if it's one on each, we call that linear regression. If it's one on more than one variable, it's called a multivariable or multilinear regression. So this model is very important, especially those that do research. I'm a researcher, and most of your colleagues who do research who consult me on these models, I really take them back to this class. So linear regression really aims to model the relationship that would make predictions or estimations based on the observed data. So regression analysis is commonly used in many various fields of economics, in social sciences, in finance, in healthcare, as well as other disciplines to understand the impact that the dependent variables have on the dependent variables. So how the independent variables, the impact they have on the dependent variables. So linear regression is given by the equation y is equal to bo plus b1 x1 plus e, which is the error term. Or you can simply say y is equal to a plus bx. So the linear regression equation can be epitomized by such a graph. Your a is the intercept. An intercept is a cutting point. So where it cuts the y-axis, that is called our a. The slope is a b, which is a gradient. And so together, this is what we call the regression equation, which is y is equal to a plus bx. So here we have an upsloping curve just to denote that there's a positive relationship. So the slope is a gradient which measures how much increase there is in y due to increase in x. So the regression also has the following properties you need to know. So relationships can either be positive or negative. So if we have a positive relationship, it is upsloping. So this is a positive relationship. If we have a negative relationship, it's downsloping. This is a negative relationship. Except that you could have a positive and strong relationship and a positive and weak relationship if the dots are far from each other. So what we use to measure the relationship, if it's positive, we use what we call R. R is a coefficient of correlation. R squared measures the strength of the relationship. So if the relationship is strong, preferably above 50%, we say it is a strong positive relationship. So relationships are measured by R, which is a coefficient of what? Determination and coefficient of correlation. So correlation is just R. R squared is coefficient of determination. So if the relationship is strong, it means they are probably above 50. So we can also have a negative relationship. R, if it's a negative R, R is a coefficient of correlation. So meaning X and Y are negatively related. But it can be a positive negative relationship. It can be a strong negative relationship and a weak negative relationship. So if it's weak, we are looking at a very minimal impact. So if R squared, for instance, is 0.9, it means 90% of Y is because of X. if you find a relationship like 0.1, it means only 10% of the independent variables affect the dependent variables. And usually in this case, y depends on what? On x. X variables are usually the independent, and y is a dependent variable, it's a result. So I'll give you a quick scenario where you're given observations x, y, and you are asked to come up with a regression equation. So I can look at the manual way. 1, 2, 3, 4, and 5. And here we have 1, 1, 2, 2, and 4. So we can complete this schedule by multiplying x, y. And we can complete this schedule by getting y squared. And also by getting y squared and x squared. So to fill in this quickly, 1 times 1 is 1, 2 times 1 is 2, 6, 8, and here we have 20. Here we have 1 squared, 1, 4, 9, 16, 25. Here we have 1, 1, 4, 4, and what? 16. Then we can total up. The total here is called the summation of x. Here summation of y. Here summation of xy. Here summation of x squared. Here summation of y squared. And our n is the number of elements that we have in each of these columns. So we have 5. So the total we're getting, we just manually total them up. So here we're getting a total of 15. Here 10. Here we have 37. Here we have 55. And here we have 26. So the quickest way you could also calculate is firstly finding the sum of squares, the variations, sum of square xx, you just have x's throughout, over n. So here we're going to have 55 minus 15 squared over 5. So here we're going to get a 10. Then you also calculate the sum of square, which is the variation in y's. Let's put y's throughout. So here we're going to have y squared is what? 26 minus 10 squared this case, summation of xy, we have what? 37 minus 15 times 10 over 5. Here we're going to have a 7. So these are some of the preliminary calculations you could have to confirm. So basically, the formulas that we are interested in is a regression equation, which is given by a plus bx, where we find our b as summation of xy over summation of xx, and to find our a as summation of y over n minus a gradient, which is b, summation of x over n, and our r summation of xy over square root of summation of xx times y. I guess I can get you.
Maybe you can go back a bit. I think I'm lost. Maybe you can just start from the summation of those variables.
Okay, so the summation of these variables, we just added up.
Okay.
So this plus that, we get 15. Here we get 10. Here we get 37. When you add them manually, These are the figures that we're getting. So this is called summation of x, summation of y, summation of xy, summation of x squared and y squared. Are we together on the totals?
Yes.
Then we have what we call the variation in x, y, and xy. This is the formula to use. So what is our x squared? X squared is 15 to the power 2 over n. Our n is 5. So 55 minus 15 squared, so 55. 15 squared is 225. Divided by 5, we get a 50, effort 5. So what we have here is 55 minus what? 45. That's how we get the 10. Then y squared is 26. Then y to the power 2, that's 100 over 5, which is 20. So 26 minus 20, we get a 6. xy here is what? 37. X times y, 15 times 10, that is 150 divided by 5, we get a 30. So 37 minus 30 is a 7. So this is why we're getting this figure here. Are we together?
Yeah, we can proceed.
Yes. And now we want to calculate the values of the regression equation. So to find our b, since summation of xy was what? 7, summation of xx was 10. So when we divide 7 over 10, we get 0.7. So where there is b, we're going to put 0.7. Then for a, since our summation of y was what? 10 over 5 minus the b we found as 0.7, and summation of x was 15 over 5. So here this will be 2 minus 2.1. So what we get is 0.1 negative. So collectively, this gives us a regression equation. Where there is a, we put negative 0.1. Where there is b, we put what? 0.7. So this is how the regression equation comes out. Are we together?
Yes, we're together.
So if they told you that if x is 10, you simply substitute it in this regression equation. So where there's x, we're going to put what? A 10. So when we put a 10 there, our y is simply going to be 6.9. Similarly, R stands for the coefficient of correlation. So our xy was 7, our xx was what? 10, and our yy was 6. When you compute this, you get a positive 0.903. So by virtue of it being positive, we know that the direction is that there's a positive relationship between x and y. It's upsloping. But when we square this, the answer becomes the coefficient of determination. So what we get is 0.816. What does this mean? 81.6% of y is because of x. So r squared measures the extent to which y is affected by x. Are we together?
Yes, we're together.
All right. So with that being said, we can now understand a few issues here. So I'll take you to an output of a regression that you need to learn how to dismantle and analyze. So it becomes a little bit tricky from that perspective. So we have tools that have been employed sometimes to simplify your work when we're doing regression, and they're able to not manually calculate, but electronically calculate these analysis for you. But what you need is to interpret the results. So we have such instances where you'll be given a question like this, and you're asked to interpret the results. So, of course, this cannot be asked in an exam to do a multilinear regression, but in this case, we're going to learn from the way the output is supposed to be produced from this. So here we have y and variables of x1 and x2. So once you input them in the data, it will produce an output that will it will look something like this. So what I need you is to learn how to interpret this data if it is produced in an output and be able to tell which one is a regression equation and which one is the R and R squared. So it is important you understand how to analyze the output that can come out, either from an Excel, Stata, or SPSS. So the first thing that you need to know firstly is interpreting the variables, as I have explained. If the input has been put, what does it mean when we have this variable? What does it mean when it comes out from an Excel sheet? Okay, so let me just show you the typical Excel output. Then we could have questions from the first. Any questions so far from what I've explained? Is everything clear? Any questions so far from what I've explained?
Yes.
Yes, what's the question?
Yes, I think I'm following.
You're following, okay. Now, the same data that we have here was inputted in Excel, and the following was the result. So I'll take you through how to interpret this result. So after are you able to see my screen?
Yes.
All right. So we have the following output. Now, if we're going to go back to our table here, at least we are able to understand a few things here. What is our N? The number of observations are what? 15.
15.
So these are 15 there. So from here, we're able to tell what is our R and what is our R squared. Multiple R is what? 0.8 what? 83. So we have a positive value there to tell us that there's a positive relationship. And what is our R squared? 0. What? 693. What does this tell us? 69 point what? 3% of Y is because of X. All together. All together so far?
Yes.
Then we're also able to identify the regression equation using the data here. Regression equation is equal to B0, which is a constant, plus B1, X1, plus B2, X2. So this is for a multiple regression here. So our constant here is what? The y-intercept. What is our constant here? 6 point what? Negative 6.202. Okay. Plus the first intercept for x1 is negative 0.376. So negative 0.376 x1 Yes,
Hello?
I can hear you.
The intercept should be a positive.
It's not always a positive. Oh, it's
Intercept
positive, yeah.
should be positive unless there's
No, my
another
screen was
reason why
deceiving
you
me.
put
You're
a
right.
negative.
Yes, yes. No, no, no. I was seeing it. It's my screen which is showing in. There was a dot there. Thank you for that. Yeah. So it's a positive, yeah. Then here we have 0 point what? 4525. So this is our regression equation. This is x2. All right. Are we together? So from that regression equation, based on our initial data, which talks about the following table, gives the per capita income of households of US dollar Y with a percentage of labor force in agriculture, which is X1, and the average schooling of the population over 25 years of age X2 for 15 developed countries in 1991. We want to interpret the data. First of all, we are told using to come up with a regression equation, which we have done there. All right. Secondly, part 2, we are being asked to find out the degree of freedom for this regression analysis. So we can find the degree of freedom from this output under the ANOVA table. You did your statistics. You remember ANOVA, right? So what is the degree of freedom that has been calculated in there? What is our degree
That's
of freedom?
14.
Is what?
14.
14. Are we all agree? Okay. So the question is, find out the degree of freedom implied for this regression analysis. So from our output here, this is the degree of freedom. So the degree of freedom is actually, for the regression, is 2. So we have 2 variables, x and y. So this is our degree of freedom. Now, under our ANOVA, if I'll take you back to your quantitative methods to test the significance of the regression line, we can use either the F significance. If we are comparing this to 5%, if this is more than 5%, we accept. If it's less than, we reject, meaning it's significant. So this one is small. We can safely say that our regression equation is statistically significant. But of course, we can use intervals to look at our t statistic based on the lower and the upper. If the figure is in between the lower and upper, we can simply say it is significant. If it's outside, it is not significant. So, of course, we cannot use the intercept to always be within range. X1, this is negative 2.8, but we have negative 0.6, negative 0.08, so it is out of range, this one. X2, we have 3.7, and 3.7, the lower is what? 0.19, and here we have 0.71. Okay, so this one is also outside. So in our narration, we need to understand how to interpret those figures in terms of their significance. So to start with, from our statistics, what we can tell is, number one, we can see that the regression output has p-values that have coefficients of both x1 and x2. So if they are less than 0.5, we can say they are both significant. So here we can see that both of them are less than 0.1. So we can simply say schooling and agriculture is significant. But if we're looking at the average years of schooling of population over 25 years, in terms of the interpretation of per capita income, let's look at in terms of per capita income, analyzing it. You can see the 0.452. 0.452. Are you able to see it?
For X2.
0.452. So in terms of per capita, what can we say regarding that? For X2, which signifies the average years of schooling, we can say that over a 25 year of age increases by 1 year, then the real per capita income would multiply that 0.452 times 1,000. The real per capita is about $452. But if we're going to look at the percentage in terms of labor force in agriculture, have you seen the 0.3 0.376? Now that one is a negative, so it implies that in a period of 25 years, an increase by 1 year will result in a decrease by 376. That's what it implies. Okay. So this is what it implies when you're using the per capita income. But generally, the whole entire regression, you'll be asked to test whether it's significant. So if this, and we're testing at maybe 5%, if this is smaller than 5, we say it's statistically significant. If it's more than 5%, it's not significant. Then you can also do the factor analysis to see which of the following is statistical or significant. You're going to see which one is out of range. If it's out of range, it is statistically significant. So here, negative 0.8, between these two ranges is outside, so this one is statistically significant. And between these two here, we're looking at the p-values. Okay, let's see. This one is in between. This one is also in between. So they're also both of them are statistically significant. So there are times when one is out of range and you should be able to interpret it in that line. So this is what this question really required. So what is the critical value at 5%? What are the exact levels of significance in the estimated coefficient? How much variation in y is explained by the variation in the equation? Also find out the total variation in y explained by the variations. So these ones are the ones I was explaining from the coefficients. One is decreasing, one is increasing. Is there an overall statistical significance by 1% of the whole regression? Yes, we use the ANOVA table to analyze this. So when it comes like that, they'll give you an output that you analyze. And if you're going to look at most of the papers, they will, let me check. They will already give you an output that is already done. Okay. So this one is a different version we're given. It's under estimation, of course, but it's a similar scenario. We have R squared, we have the F, the significance is at 0.01, and be asked to analyze that. Okay. So far, any questions on this?
Maybe you just go through quickly, just from, I'm sure A we are done, just on the same significant figure. There are sometimes when they ask about the zero value, if the statistical is not equal to zero, something, I don't know what they mean.
There are times when we are looking at if our B or our R is equal to 0, it means there is no relationship at all. So the relationship using the B, maybe it's the one that you're talking about.
Then there are sometimes when you I don't know what they mean. I've seen in that table you gave us. There is the T star. Is it T statistic? There is also T tab. There is also T calculated.
Okay.
I don't know what the difference is on those.
Maybe when I look at this, it will open up what you may be asked. Okay. So let's look at this question here. We are told that food products of a company are recently introduced. A new line of soft drinks in Lusaka and Copperbelt. Based on the drink's apparent success, the company is considering a nationwide launch. Before doing so, it has decided to use the data collected in the 2-year market test to guide in setting the prices and forecasting the future demand. The firm has collected data in total from 48 observations through various stores, and each of these consists of data on quantity depended and the number of drinks purchased per week and price per drink, and competitors and average price per drink and income and the population. The company forecast has run a regression data and obtaining the following results. So this is the result in here. So now the questions follow from what I've just been talking about here. So let's see the follow-up questions and see how we can answer them. So question number 1, we've been asked to identify which of the explanatory variables in the regression are statistically significant. So how do we tell which of the variables is statistically significant? So let's look at them in terms of the following. Let's look at the constant. The constant here, the coefficient is what? Negative 4516.3. Okay. So we can divide this by the standard error. We're going to get a value which is 0.905. So which of these values are statistically significant? So let's calculate to get the t values by getting the gradient over the standard error. So we're just dividing this divided by that, we get the dash there. So what that means, it's the t value. Okay. Then when we go to on price, we divide 3590.6 divided by 702.8. So when you divide that, we're going to get our statistical value, which is negative 5.1. We also go here under competitor's price, we divide the slope divided by that, we're going to get 4.9. We also go to the income, we divide our 7.77.1 divided by 6.4, we get 11.7. And also we check here on the last figure, we divide for the population 0.4 divided by 0.31, we're going to get 1.29. Now, of these figures, which ones are significant. And how do we know the significance? So at 5% significance, the critical sample size that we've been given here is what? How many observations were collected? What is our sample size?
Observation of 48.
48 sample size, yes. Then we want to look at the critical values. So for us, following the results that I've been telling you there, we look at the values that are the calculated T that is higher than the critical T. So we'll be comparing these two. So which ones, the ones that are critical are the ones whose computation is higher. So we're looking at 5%. So here you discover that we have on price, which is higher. We have competitor price, it's also significant. We also have income, it's also significant. All values that are below that are insignificant. So when we divide these figures there, if you're not given a percentage, we usually use the standard of 5%. So we first divided
Excuse me, sir.
this by that. So the figures that we're getting, let me use the pamphlet so that I'm quick on the figures that were calculated. So when you divide this divided by that, this divided by that, this divided by that, these are the figures we're getting here. For the first one, it is 0.9. It's less than 5%, so it's not significant. This one is 5.1, so it's about 5%. All right. This one, of course, it's less than 5, but it's almost 5 if you round off. It's significant. This one, when you divide that, it's more than 5. It is significant. This one is not significant. It's 1 point something. This one is not significant. So these are the three significant ones at 5%. So when we're going to compute this and we're going to compare them, we are going to find the significant ones there: on price, income, and competitor price. And the next question that is being asked is, explain the variation in drink sales that explains the model. So we use R squared here. To what extent? So we need to interpret this 93%, like I explained to you. So it means that 93% of the total variation in drink sales is explained by the regression model. So this is where the R squared comes in. So we explain the regression model and its significance using our R squared. If it was 0.03, it would mean 3% of the overall regression is explained by that. Then we also go to second part, compute the price elasticity of demand for the drinks at the firm's mean price of 7.5 and the mean weekly sales of the quantity 20,000. So here we first come up with the regression equation, which is computed from the variable that we have here. So we have the constant, so 0.4516.3, that's a constant which will come here. And the first variable that we have, we can we're looking at the drink, so on price, that's px, so it's minus 3590.6. So that is where it's coming from here, minus 359.6. That is price of its own price. This is good x against good x. Then we look at the other variable that we have, the competitors. It's a positive 4226.5. So we can call this EY if you want, competitor's price. So that's where the variable is coming there. So we put it here. That's where it's coming from. Then the income, we have that. Then we also have, lastly, the population, Sometimes you can use N for the population's income is that these are positive. So this is where the regression equation or the demand function is coming from. Are we clear on the demand function?
Yes, yes.
So this is
I don't know
captured
others.
from the class we had. Remember what the similar class on this one, right? So the variables are coming there. So to find the elasticity, we just get the gradient for the good X, dq over dp. Where's the gradient? This one here, 359. We put this gradient there. Then the price of good X has been given as 7.5, and the demand is 20,000, which was given. So we calculate that by getting a negative 1.35. What does it imply? It implies that demand is elastic. If it was exactly 1, we would demand that demand is unitary. If it is less than 1, we say that demand is inelastic. For cross price elasticity, we're looking at the gradient for the competing price. So here the gradient is what? 4226.5, which we have here. And the competing price is what? 6.5. So the cross price elasticity we've been given, the competing price is 6.5 here over the demand of 20,000. How do we calculate the 20,000? We're given the total 20,000, but even if you're going to fuse these figures into the regression equation to give you 20,000. So it is easier when you're given there. So to find cross price elasticity, we now use 6.5 over 20,000 here. So we're going to compute this, which is 1.37. So here we know when we have a positive cross price elasticity, what does it mean? That these are what? Substitute goods. If we had a negative, we would say they are what? Complementary goods. You remember that?
Yes.
So we also go to income. When we calculate and we get a positive answer, this implies that it's a normal good. Of course, this is more than 1. What type of a good is it to be specific? It is a luxurious good because it's greater than 1. So this is now a combination of everything that I taught you just based on this. So we are done with our linear regression, estimation, and forecasting. Unless there are any questions, we end here.
So when you find these T calculated, I mean the critical values, you compare them to the 0.5 always.
Yes and no. Okay, 0.5 is the easier one for you to understand. But in actual sense, you're supposed to even use a T table where you're going to read the readings corresponding. So if our degree of freedom is, how many are they here? 1, 2, 3, 4. So you subtract 48 minus 4, then you read under 5%, under 44, you find the T reading, then you separate. But for the easy understanding of you guys, we just compare them up 5%. The figures that are below 5% are insignificant.
Okay.
Yeah.
Mr. Fernand,
Yes, yes.
I would appreciate if you can also 2019 question that you